In section 3.10, we are going to be talking about derivatives of inverse trigonometric functions. You do not need to memorize these formulas. Right now, I just want you to be able to work with these formulas and just understand how to use them, practice with them in the homework. I am not going to be putting any of these on the test. So you do not need to memorize any of them and worry about having to know any of them for the test. I just want you to be aware that these formulas are out there and just have a little bit of practice using them. I am going to show you how one of them is derived. All of them can be derived similarly. If for any reason you did have to come up with one of them off the top of your head and you didn't memorize the formula, there is a way to figure out what the derivative of an inverse trigonometric function is, just using what we already know about basic trigonometry and then what we already know about just basic trig derivatives and also implicit differentiation. We can put all three of those ideas together and come up with derivatives for inverse trigonometric functions. So I'm going to show you that first, but then I'm going to go through the inverse trig derivative formulas and do a few examples. So here in this example, what I want to show you first is how we can come up with the derivative for inverse sine of x. Now, from trigonometry, inverse sine means that I know the sine value and I want to figure out the angle that has that sine value. So sine inverse of x is equal to some angle theta. That's just a trigonometric formula. Sine inverse of x is equal to some angle theta. So if we rewrite this as a normal sine function by moving it to the other side, that means x is equal to sine of theta. And we can draw a triangle that exhibits this behavior. Usually sine is a fraction. It represents the sides of a right triangle. It represents the opposite over the hypotenuse. So I can rewrite this as a fraction by putting it over 1. And I'm going to label this angle as theta. And this fraction is telling me that the opposite side is x and the hypotenuse is 1. And that means that by the Pythagorean theorem, we could figure out this other leg. So x squared plus that question mark squared is equal to 1 squared, which means question mark squared is equal to 1 minus x squared. So our question mark side is the square root of 1 minus x squared. So this triangle is representing this x equals sine theta expression that we have. So in x equals sine theta, we can do implicit differentiation. If we go through and differentiate everything with respect to x. So the derivative of x with respect to x is 1. The derivative of sine theta, now that's going to be a chain rule. It's going to be cosine theta times the derivative of the inside, which is d theta dx. Now d theta dx is what we're trying to figure out. Because remember, this was equivalent to this. We're trying to figure out d theta dx. So if I solve this for d theta dx, I get 1 I get d theta dx equals 1 over cosine theta, which is secant theta. So d theta dx is just secant theta from our triangle. So look at your triangle. D theta dx is just whatever secant theta would be on that triangle. Now secant is hypotenuse over adjacent. And that's just something we need to remember from trigonometry class. So hypotenuse over adjacent. So what I have just figured out is that the derivative for sine inverse of x is 1 over the square root of 1 minus x squared. Using all sorts of crazy rules that we learned in trigonometry class. There's some algebra thrown in there with the Pythagorean identity. There is some basic derivatives and some implicit derivatives. Stuff from 3 different classes. So it's pretty crazy. But it is possible to derive the formulas. Most likely, though, it's not just going to be a plain old x in that formula. It's going to be something different. So let's just go through the formulas really quickly. And we want to think of these formulas not just as having x as the angle, but possibly having anything inside that angle that we might have to deal with. So I'm not going to write x in here. So sine inverse of u, and u can represent any function of x. So we would have to possibly treat this as a chain rule, which means we're going to do u prime over the square root of 1 minus u squared. That follows the exact same pattern we just saw above. The only difference is, because of the chain rule, we have to multiply by the derivative of the inside stuff, which is why we have u prime in the numerator. Now for cosine, the only thing different with cosine is we have a negative in the front. And if we went through the whole proof like I did above, you would see why. And it turns out when we do our implicit derivative here, we would have x equals cosine theta, and the implicit derivative would be 1 equals negative sine theta d theta dx. So that's where the negative comes in. Everything else ends up the same. For tan inverse, the derivative for tan inverse is u prime over 1 plus u squared. The derivative for cotangent inverse is exactly the same, but a negative. U prime, negative u prime over 1 plus u squared. The derivative for secant inverse is u prime over absolute value of u times the square root of u squared minus 1. And then if you haven't seen the pattern yet, you might be able to guess what cosecant's going to be. It's going to be the exact same as secant, but with a negative. So again, you do not need to memorize these right now. This is something that we work a lot more with in Calculus 2. So again, right now, I just want you to get some practice with them. I just want you to do some homework problems with them. Just know that they exist, and there is a way to derive them just using some basic trigonometry and some implicit differentiation. And these will not be on the test. So we're just going to go through a couple of quick examples with them on how to use them. The reason we have a u in here is because this might not be just a plain old x. It might be x squared or 5x or 3x minus 2. U could be a function of x. Which means we have to do chain rule, and that's why we have the u primes in the numerator. So I just want to do a couple of quick examples. We want to calculate each of these derivatives. We are going to do the derivative for cosine inverse of 5x. So our u here is 5x. So with cosine inverse, we do u prime in the top. U prime is going to be 5. So when we do our derivative, cosine inverse is going to be negative u prime over the square root of 1 minus u squared. It might also be beneficial to write out what u squared is going to be. Now be careful, because when you square something that's got two factors there, both factors are going to be squared. So u squared is actually 25x squared. Both the 5 is going to get squared and the x is going to get squared. So 1 minus 25x squared. The derivative for tan inverse of x squared plus 2. So in this case, u is x squared plus 2. du is 2x. And for u squared, I'm not going to FOIL that out. U is a binomial. When it comes time to do u squared, I'm just going to put it in parentheses with the squared around it. So tan inverse is positive. And in the top, we have u prime. And in the bottom, we have 1 plus u squared. So I'm just going to put my u in parentheses and put a square on it. You could FOIL it out if you want. Really not necessary. Doesn't really matter. The derivative for cosecant inverse of, let's say, e to the x. So here our u is e to the x. U prime, the derivative for that is also e to the x. The formula for cosecant inverse is negative u prime over absolute value of u times the square root of u squared e to the x squared. When you have something that already has a power and you want to raise it to another power, those powers get multiplied. So this is e to the 2x. So we're going to have e to the 2x minus 1. Now, we don't necessarily need absolute values on this e to the x in the bottom because e to the x is always positive. And I know that because I remember what my e to the x graph looks like. E to the x looks like that, and it's always above the x-axis. So it's always positive. So the absolute values are not necessary, which means this e to the x can cancel with this e to the x. So we could simplify this one a little bit, and we could just say negative 1 over the square root of e to the 2x minus 1. So I just want you to be aware that these formulas exist. You do not need to memorize them. You do not need to be able to derive them. We will work with them a lot more in Calculus 2. Just practice with them for now. The important thing is to recognize the u chunk and the u prime, and just being able to pull out those puzzle pieces and work your little magic and be able to put the formula back together with them to figure out what the derivative is going to be. The inverse trig derivatives will not be on the test.